In this module, we will solve the modified radial equation by the factorization technique. As you already know that we started with electronic Schrodinger equation, and this equation ultimately had many terms. The first two terms represent the radial part, while the last two terms represent the angular part. By solving the angular part, we got theta theta and phi phi, and their product is called the spherical harmonics. But the first two terms, they are called the radial part. We took that radial part and modified it, and ultimately we have been able to modify this radial equation, which is shown here. This equation, as you can see here, is del 2 by del r square plus w plus k by r minus L into L plus 1 upon r square, parenthesis closed, Fl is equal to 0. Here, as you remember, we discussed in the last module, Rr is equal to Fl by r, whereas W is 8 pi square mu upon h square E electronics, and K is equal to 8 pi square mu h square Ze square upon 4 pi epsilon 0 is equal to K. That's basically the K. Now, this equation can be factorized. So now the question comes, how to factorize this equation? So that's basically what we will be now working on. To solve this equation by factorization technique, we introduce one is RL plus. Notice it carefully. This is d by dr plus k by 2l minus l by r. This is called creation or step up operator. And second operator is RL negative, which is d by dr minus k by 2l minus L by R. This is in parentheses, and this is called annihilation or step down operator. Now, we take these two operators and operate it on Fl. As you can see here, that RL plus dot RL negative, when it is operated on Fl, one gets the expressions. You can see this operator has been solved through the number of equations, as you can see, in a very systematic way, and ultimately after doing all this, we get this equation, which is RL plus RL minus Fl equals d2 by dr square minus k by 2l whole square plus k by r minus L into L plus 1 upon r square, parenthesis closed, Fl. So this is the equation which we get through this operation. Now to this equation, we add and subtract W. And W, you know already, is equal to 8 pi square mu upon h square E electronics. So once we add and subtract W, this equation gets further modified, and we have the equations, which now becomes RL plus RL negative Fl is equal to d2 by dr2 plus W plus k by r minus L into L plus 1 upon r square, parenthesis closed, minus W plus k by 2l whole square, all in parenthesis Fl. So this becomes our this equation. And as you can see in this equation, the first equation, that is d2 by dr2 plus W plus k by r minus L into L plus 1 r square, is equal to 0. We have shown it earlier. Therefore, our this equation ultimately reduces RL plus RL negative Fl is equal to minus in parenthesis W plus k by 2l whole square fl. So this is a very important equation. But please remember, in a box we have already shown that for L we have the equation which is d2 by dr square plus w plus k by r minus L into L plus 1 upon r square, Fl is equal to 0. Similarly, if L is L minus 1, the equation gets modified. And if it is L minus 2, the equation has a different form. So this point we have to keep it in mind. And now once we have got this equation, RL plus RL minus FL is equal to minus W plus K by 2L whole square, then in parentheses, and then we have FL. Now we operate this equation with RL negative, and once we operate this equation with RL negative, and as you can see here, we do some manipulations. As you can see here, we are modifying the equations through various steps. Ultimately, we are getting the equation which is shown here, and that is RL negative RL plus FL minus 1 is equal to minus W plus K by 2L whole square FL minus 1. This is very, very important. So this is the equation which we are now getting. If we compare this equation with our earlier equation, we straightway get a simple relation, that is RL minus is when it operates on FL, we get FL minus 1. So now you can understand why we call RL minus to be annihilation operator. Because when it operates on the function FL, it leads to the function FL minus 1. That means one value lower. So this is a very, very important point, and we will be using this later on. Now if we operate equation RL minus RL plus FL minus 1 equals minus W plus K by 2L whole square in FL minus 1 with RL plus, then you can see we get this equation, and this, if it is compared with our earlier equation, we will get RL plus FL minus 1 is equal to FL. So here, when RL plus, which is called a creation operator, when it operates on FL minus 1, it gives you a one value higher function FL. So now you can understand why these two operators are called step up or step down or creation or annihilation operators. Now one can ask the question, what is ultimately we are getting out of this? This is important because now try to see, suppose that the maximum value of L which is allowed is L maximum. Suppose that. It means that if you have a function FL maximum and on it if you operate a creation operator, then it should give in principle FL max plus 1, but that cannot exist because maximum value is L max. Therefore, output should be 0. That means R plus L max plus 1, when it operates on FL max, it should give equal to 0 value. On this equation, if we further operate minus L max plus 1, we get the equation RL max negative or negative L max plus 1 or positive L max plus 1, FL max is equal to 0. If we compare it with our earlier equations, which we had done earlier, we will notice that RL negative, RL plus, FL minus 1 is equal to minus in parenthesis W plus K by 2L whole square FL minus 1. And therefore, for L max, this equation, this is a very important equation. You notice at this that this is RL max plus 1 with negative operator, then R plus L max plus 1 FL max is equal to minus W plus K by 2L max plus 1 whole square FL max. And from this you can very well see that if we compare it with our earlier equations, ultimately it will lead us to the expression W plus K by 2L max plus 1 whole square is equal to 0. That means W is equal to minus K square upon 4 L max 1 whole square. And if we denote L max plus 1 by N, then therefore W becomes equal to minus K square upon 4N square. And W, if you remember, we have already made the substitution. This W is basically equal to 8 pi square mu h square upon into E electronics is equal to W. And you also know K is equal to 8 pi square mu upon h square into Z square upon 4 pi epsilon 0. If we make these substitutions as we are doing it here, and if we rearrange it, you can see here we are getting E electronic, which is the electronic energy of the hydrogen atom. And this is minus 2 pi square mu z square E4 upon n square h square 4 pi epsilon 0 whole square. So this is the energy which we get. Here please remember that n is what we call as the principal quantum number, and its value is L max plus 1. Or in other words, we can say that L can have values from 0 to n minus 1. One thing which you can notice from this expression for electronic energy, that the electronic energy of hydrogen atom depends only on the principal quantum number, because it's proportional to 1 upon n square. So this is very, very important point which one needs to keep it in mind. Other quantum numbers which we have introduced, L and M, they do not affect the energy. That means the electronic energy. After having found out electronic energy, now we will try to find out the corresponding radial part. And for this, we will use the expression which we derived in the course of our study, and that is R plus L max plus 1 FL max is equal to 0. This we have said already, because creation operator, when it operates on the function with the maximum value, the corresponding output will be, answer will be 0. But here we should remember that R plus L max plus 1 would be d by dr plus k by 2 into L max plus 1 minus L max plus 1 upon R. That's basically the expression for R plus L max plus 1. And then L max plus 1 is n. Therefore, our Rn plus becomes d by dr plus k by 2n minus n by R. And now when it operates on FL max, as you can see here, this is 0, and then if we solve this equation further, ultimately we get the expression dFL max by FL max is equal to minus k by 2n minus n by R dr. And then if we integrate it, ultimately we get the expression for FL max, which comes out to be FL max is equal to R raised to the power n into e to the power k by 2 nr. And we already know that FL is equal to RR multiplied by R, and therefore From here one can get the value of radial function for n and L max, which is a function of r, that will become equal to r raised to the power n minus 1 e to the power k by 2n into r. So now we have been able to get the expression for the radial function. Radial function depends upon n and L, and this expression is for r n L max. And if we have to normalize it also, then suppose n is the normalization constant. Therefore, then this becomes n into r raised to the power n minus 1 e to the power k by 2n r. Now in this equation, we need to find out the value of the normalization constant n. Of course, we will find out the value of the normalization constant, but besides that, if you look at the term kr by 2n, we substitute here the values of the k, which is 8 pi square mu upon h square z square upon 4 pi epsilon 0 into r by 2n, and that's basically simplifies to give you z into mu e square upon h square 4 pi epsilon 0, where h cross here is h upon 2 pi. And if we simplify it here, this becomes kr upon 2n is equal to zr upon na0, where a0 is mu e square upon h cross square 4 pi epsilon 0 raised to the power minus 1. This is nothing else but what we call as Bohr radius. Let it be a small exercise for you. Show that Bohr radius has the units of length. This you can do it yourself. And once we do this, our ultimately equation, as we have already defined, is r n L max r, and that's basically equal to n r raised to the power n minus 1 e to the power minus zr upon n a0. So now instead of kr by 2n, we have put zr by na0. So that's basically the final expression for the radial function. Except one thing is missing, and that is to find out the value of the normalization constant. And that's basically what we will do in our next module. However, at this stage, I would like to make a mention of one very important thing, that the expression which we just mentioned is basically for L max. However, if we have to find out the radial function for the values lower than the L max, for that basically we will use the property of the annihilation operator, and that's that r minus L, when it operates on FL, it gives you FL minus 1. So once we get the radial function for L max, then for subsequently other L values, by applying annihilation operators, one can get the radial function for other values of L. So in this module today, we have solved the radial equation to get the corresponding radial function. In the last module, we took radial equation and reduced it to a form which can be factorized. Today we started with that equation, introduced the two factors, creation and annihilation operators, and using them, and then through certain modifications, we found that one can get the radial function. And the expression which we got for the radial function was Rn for maximum value of L, that means L max is equal to n into r raised to the power n minus 1 e to the power zr by na0. Here please remember that A0 corresponds to the Bohr radius. And we also today got the expression for the electronic energy, and that is E electronics is equal to minus 2 pi square mu z square E4 upon n square h square 4 pi epsilon 0 whole square. So that's basically what we have got today. And we also saw that the radial part depends on two quantum numbers, that is the principal quantum number n and the azimuthal quantum number L.